Okay, in this video, I'm going to continue section 2.2 and take a look at our next few example problems. Before we do that, there's two rules I want to talk about. Your constant multiple rule. If you actually have a constant in front of your function, when you go to find the derivative, what you can actually do is pull that constant out front and then just find your derivative of your function and then multiply your constant through, right? And we'll see that kind of as we go through some of these example problems. And then the sum and difference rules. If I have two functions that I'm adding or subtracting together, what I can do is I can actually find the derivative of just the first function, the derivative of just the second function, and then the sign will stay the same in between that. This will be super useful when I want to find the derivatives of polynomial functions and I have a bunch of terms. I'm going to basically look at each term separately. And that's what we're going to do in our first example. Example 5, I want to take a look at the derivative of f of x. So what I'm going to do is the derivative of f of x, first I'm just going to look at x cubed and I'm going to use my power rule. So bring my 3 down front, x squared, and then decrease my power by 1. Same thing for the minus 4x. If I look at just that part, I'm going to, technically have an exponent of 1, so I'm going to multiply that by 4, and then decrease the power of 1, so it really becomes x to the 0, which is 1. And then my derivative of my constant function, which is 5, is really just 0, so I'm not going to write it. So my derivative would just be 3x squared minus 4. For g of x, I'm going to first rewrite the first term. So I have negative 1/2 x to the 4th plus 3x cubed minus 2x. Now when I find my derivative, I'm going to use my power rule 3 different times. So my g prime of x is going to be negative 2x to the 3rd plus 9x squared minus 2. So that's going to be my derivative of g of x. For time purposes, I want to skip example C. It's not that it's hard, it's just lengthy. But what you can do if you want to try this on your own, then the derivative comes out to be 5/2 x to the 3/2 minus 9/4 x to the 1/2 plus 7/4 x to the negative 1/2 plus 5/4 x to the negative 3/2. Again, very doable, but I just want to take a look at other example problems. All right, example 6. I need to find the coordinates and equations of any horizontal tangents. All right, so in order for a function to have a horizontal tangent, that implies that that slope is going to be 0. Because a horizontal line always has a slope of 0. So if I want to do my curve, I want to find the derivative of my function. So I'm going to start with y prime and use my power rule. So I end up getting that y prime is 4x cubed minus 4x. Now in order for me to see when horizontal tangents are, is I want to see when I have a slope of 0. So remember, this is my slope formula at any x value. All right? So this time I'm giving you what I want my slope to equal. I need to find those appropriate x's. So I'm going to say that I want my derivative to equal 0. And I want to figure out when that's going to happen. So what I can do is I can actually pull out a 4x. Then I can keep factoring. So therefore, based off of this, I know that at x equals 0, at x equals 1, and x equals negative 1, all of these are going to have horizontal tangents. Okay? Because at each of those points, the slope is 1, the derivative is 0. Excuse me, the slope is 0, the derivative is 0. And I also need to find the y values. So when I plug 0 in, I end up that y value is 2. When I plug 1 in, I get that the y value is 1. And when I plug negative 1 in, I get the y value is 1. Remember, to find these y values, we are going to plug into the original y equation. All right. Let's take a look at another example. I want us to remember, at any point of tangency, a function and its tangent line share two things. They're going to have the same y value because they're going to share a point, really. So they have the same x and y value, okay, because they're going to share a point. Also, they're going to have the same slope. At that specific x value, right, they're going to have the same slope. So I need to use both of those information to actually help me solve example 7. I want to find the values of k such that the line is tangent to the graph of f of x. All right. So what I first started with was I looked at my line and I rewrote it. So my line was y equals negative 5x minus 9. So I know that my slope is negative 5. So that's going to be the slope of f of x at x equals c. I still don't know that. All right, so that's my slope is going to be negative 5. I don't know exactly where this is happening yet. What I did next was I found what f prime was, because f prime is also my slope formula. That's my instantaneous rate of change. So that gave me 4x plus k. Okay. So that gave me 4x plus k. Now, at the spot that I'm concerned about, I know that my slope is going to be negative 5. So negative 5 then equals 4x plus k. I'm going to be able to use that a little bit later. So now I know that my k is really negative 5 minus 4x. All right. So what I want to do is I want to find the values of k so that the line and the graph, the line is a tangent to the curve. Right? Now, I also know that in order for them to be tangent, if that line is a tangent to that curve, then they have to intersect at that same y value and also the same x value. So that means that 2x squared plus kx minus 1 will equal negative 5x minus 9. They're intersecting. They're intersecting at my point of tangency. Okay, so it's intersecting. Now, even though this equation has two unknowns, I can use substitution and plug what k is in. So I get 2x squared plus my negative 5 minus my 4x, x minus 1. So then I end up getting 2x squared minus 5x minus 4x squared minus 1. So then I end up getting negative 2x squared minus 5x minus 1. So I get negative 2x squared plus 8 is 0. So if I keep solving this down, factor that out. So what this tells me is at x equals 2 and at x equals -2, then my slope will turn out to be -5. Okay, that is true. So at these 2 points, however, that is not what the question was asking. If we take a minute and scroll back up, the question is asking find the values of k. So what I need to do is if x is 2 and -2, I need to plug it into this k definition. So it turns out that my 2 k's are -13 and 3. So there's actually going to be 2 parabolas, 2 different parabolas that'll both be tangent to that line. Derivatives of sine and cosine functions. I'll go through how to prove one of these, but I won't do both of them. So the derivative of sine is cosine, and that's one we're going to actually prove. And then the derivative of cosine is negative sine. So hopefully once you see one proof, you'll just believe the other one. If not, try it on your own. All right, so I'm going to prove this guy. So I have the limit as delta x approaches 0 of sine of x plus delta x minus sine of x all over delta x. Now that is a sum formula. So I break it apart and say it's the limit as delta x goes to 0 of sine of x cosine of delta x plus cosine of x sine of delta x minus sine of x all over delta x. Now I'm going to do some grouping so that I can pull out a sine of x. So what I'm going to do is I'm going to pull out a sine of x, make that a little neater, from my first term and my last term, and I'm just going to hang on to the other stuff. The reason I'm going to group them is they both have sine of x, whereas the other one has sine of delta x. All right. Now what I can do is I kind of want to separate that stuff out. So I'm going to have, I have the limit, delta x goes to 0 of sine of x cosine of delta x minus 1 all over delta x. And then I have plus cosine of x sine of delta x over delta x. And then what I can do in each of these is I can actually put my delta x with whichever term it's going to be more helpful. So I want to just think about it. So I'm just going to kind of rewrite this so that I have, it's really sine of x times cosine of delta x minus 1 over delta x. And then plus cosine of x times sine of delta x over delta x. So I haven't really changed much. I just kind of wrote it a little bit differently, and I think it's just a little bit cleaner because the 2 in my parentheses are 2 that I have memorized. The cosine of delta x minus 1 over delta x as delta x goes to 0, that's going to become 0. So now I can actually plug in delta x. So when I plug in delta x, I get that it's a sine of x, and then this thing, the cosine, that actually just becomes 0, plus the cosine of x, and then the sine of delta x over delta x becomes 1. The first half goes away, and I'm just left with cosine. Again, you can use a similar argument to prove that the derivative of cosine is negative sine. So let's look at a few examples. So if I wanted to find these derivatives of these functions, in the first one, it's a constant. So what we can actually think about, we're going to kind of imply that rule that we first talked about. We can actually pull that out front and then just find the derivative of sine. So we could just say that y prime is going to be 2, because that carries through, times cosine of x. In B, I might rewrite it so it's 1/2 sine of x. And again, I can use that constant rule and just say it's going to be 1/2 times the cosine of x. In C, I want to do each term separately. So y prime of x, I'm going to use my power rule. There's an exponent of 1, that drops down, so it's going to turn out to be 1. And then it's plus, and then the derivative of cosine is actually minus sine. All right, so just to kind of wrap things up and remind us before we meet again, the derivative of a function at any 2 points gives us 2 equivalent things. It gives us the slope of the tangent line at that point. Derivative is slope. It also gives us that instantaneous rate of change at that point, because remember, rate of change is a slope. Since it's instantaneous, it's exactly at 1 point instead of average, which is what we're used to.